Okay, so today we're going to be talking about something called momentum. All right, so momentum is something that has actually been thrown around in class by a few people, and I want to make sure that everyone knows exactly what momentum is. So what we're going to do is we're going to start off with Newton's second law. Newton's second law, F equals mass times acceleration. Okay, we are all familiar with this one. We've used it a lot. F is equal to mass times acceleration. So what exactly is acceleration? Well, we know acceleration is equal to a change in velocity over a change in time. So we could rewrite that as being a final velocity minus an initial velocity over time. Okay. Well, I'm going to plug that in to our formula over here. I'm going to change colors that way you can see exactly what I have. So we have um, mass times Vf minus Vi over T. Okay, and that equals force. All right, force is equal to mass times this change of velocity over time. Okay, I'm going to multiply the time over to the other side because I hate fractions. So what we have is F times T equals, and we still have mass times, you can see I'm having fun with colors, Vf minus Vi. All right, so we can take all this out and take a look at what's inside the parentheses and distribute it out. So force times time is equal to mass times the final velocity minus mass times the initial velocity. There we go, initial velocity. All right, so we have this thing that says, okay, force times time is equal to this change in whatever this quantity is, this mass times velocity quantity. Okay, well, that's what we're going to call momentum. Momentum is denoted by a lowercase p. For whatever reason, maybe we started running out of letters. So P is equal to mass times velocity. Mass times velocity, that is momentum. So that means if we're showing this, that means a force is equal to a change in momentum, delta P, over a change in time. That's another way of writing force, a change in momentum over a change in time. And this right here is actually how Newton first formulated his second law. He formulated it in terms of momentum, not in terms of acceleration. We just get to acceleration first and before we get to momentum. So we give it to y'all as F equals ma, but it means the exact same thing, change in momentum over the change in time. Now, what exactly is momentum? Well, I like to say that momentum is inertia in motion. Okay, inertia in motion. That is momentum. We know that inertia is a resistance to a force. It's a resistance to that acceleration, right? M up here is almost a measure of the amount of inertia that something has. It takes a greater amount of force to get something moving if it has a larger mass. Well, what if it's already moving? What if it already has a velocity? So momentum is talking about, okay, if it already has a velocity, how much effort is it going to take for me to change that velocity? So momentum is inertia in motion. Okay. Now we also have this other thing over here. We have it force times time. So we're going to give that a name as well. We're going to call that impulse. Okay, impulse. I-M-P-U-L-S-E. That is impulse. So impulse is equal to force times time. And that one is also given a funky letter. It's given the letter J. I like to call it Jimpulse. So force times time. So that means in this formula right here, we can say that impulse is equal to, and I'm actually going to write it out. So impulse is equal to the change in momentum. Okay, so you change your momentum, that is equal to impulse. And impulse relies on a force and how long that force is being applied to an object. So the force multiplied by the time gives us the change in impulse. All right, so let's see if we can do some work with these new equations. All right, so we have a bowling ball. Okay, there's a nice bowling ball. You can get some holes in here. All right, bowling ball. And the bowling ball is rolling down. and it has a velocity of 2 meters per second, and it has a mass of 8 kilograms. Okay, so what is its momentum? Well, momentum is equal to mass times velocity, which is 8 kilograms times 2 meters per second, which gives us 16. And what's the unit here? What's the unit for momentum? We have a kilogram multiplied by a meter per second, so we call it a kilogram meter per second. I know what you're thinking. This looks very familiar. It looks like the unit for newtons. Well, you're missing a squared down here, right? Kilogram meter per second squared is a newton. It looks like a joule, but a joule is even more with a kilogram meter squared per second squared. So this is a very similar unit to all those, but it's describing something different. Momentum is a vector. Momentum is a vector because it's mass, which is a scalar quantity, multiplied by a vector here in such a way that we maintain the vector. So you can have so much momentum this way, or you can have so much momentum that way. It's dependent on the motion of your body. And so we actually set it apart from energy and from force by almost leaving this unit alone. So we don't have a specific name for this. The unit for momentum is just kilogram meter per second. And that's what we're going to have to say. So it's kilogram meter per second. Okay. Now, what if this ball, this bowling ball, maybe it misses the split that you were trying to pick up and hits a wall, and exerts a force on that wall. Maybe it's in contact with the wall for a time period of 0.02 seconds. So the question is, what is the force? What is the force that or the ball is imparting onto the wall? Well, we know that force times time is equal to this change in momentum, right? mvf minus mvi. Well, if it hits the wall and it stops, then we can say that the momentum afterward, the final velocity, is just 0. So that gives us that the force times the time is equal to mass times velocity initial over the time that it's in contact. Well, we've already calculated this. Mass times the initial velocity is this 16 kilogram meter per second, and we're going to divide it by 0.02 seconds. Okay, and that should give us a force. So the force that we get from this, if you plug that in your calculator, is 800 newtons. And I'm actually missing something. There's a negative here, so we have a negative that follows this 16. So we end up with a negative 800 newtons. Now, why is it negative 800 newtons? Well, the ball is moving with a velocity that is going this way. What does the force have to be to stop it? This is the object's velocity. The force has to be exerted in the opposite way to stop the ball. So this is telling us that it is a vector quantity and the force is a negative 800 newtons. Okay, so let's take this even further. And let's say that we have a car. I'm going to try my hand at drawing a car. It's not horrible. All right, and here is window. There's another window, and there you are. You are driving. Yay! All right, so you have your car. I guess it needs some wheels. You have your car, and maybe you miss a turn in the road or something. You're not paying attention, and there is a wall that you are going to crash into. Okay, so you have a mass, maybe a mass of 1,200 kilograms, and you're maybe moving with a velocity of 30 meters per second. Okay, so you have quite a bit of momentum here. So the question is, what kind of force is going to be delivered onto you the person in the car, when you hit this brick wall? Well, we know that the force times the time, just like what we saw earlier, is equal to mvf minus mvi. Now, if you hit the wall, you're more than likely probably going to stop. You may roll backwards, but if you hit the wall, you're probably going to stop. So this is going to be going away, just like it did earlier. So now we have something that says force times time is equal to negative mvi. Well, this right here, you can't help. You have that mass, you have that initial velocity. This is going to be a constant. So over here, we can do some manipulations. So we can have a really large force exerted for a really small amount of time. And that can give us a mass times velocity of, what is this, like, well, 30 times 1200. I'll let you do that. So you can have a really large force exerted for a really small amount of time, and you can have this momentum. Or you could have a really small force over a very large amount of time. Now, here's a question for you. Which one would you rather have? Would you rather have an extremely large force exerted for a very small amount of time, or would you have a very large, or excuse me, a very small force exerted over a really large amount of time? Which one would you prefer in a car accident? Because both of these are going to equal mass times velocity, and specifically mass times initial velocity. Which one would you rather have? Well, I would much rather have this one. Right? Think about that. Think about that in terms of a car accident. What is it in a car accident that could make the time that the force is applied larger and therefore make the force that you feel shorter? Think about a car accident. What could do that?